Alright, so where we left off last class, we had learned how to draw and interpret bond line structures. In our first class, we learned how to calculate the formal charge. In a Lewis structure, this is easy because we have all the non-bonding electrons. In our bond line structures, we do not include the lone pairs. So what we need to do is we need to figure out what is the formal charge on the atoms in our bond line structure. Because if we don't include a formal charge or the lone pairs, we have one or two scenarios. So here for the nitrogen, it could be negatively charged and have 4 non-bonding electrons, or it could be positively charged and have only one lone pair. Chemists have adopted the convention of including the formal charge. So if we have the formal charge, we can determine the number of non-bonding electrons. In order to determine the number of lone pairs on the atom, we can first determine the appropriate number of valence electrons for that atom. And then when we examine the atom, we have to see if it actually exhibits the appropriate number of electrons. So for oxygen, it has a valence of 6. We can also learn to recognize certain patterns. For oxygen, when we have 1 bond and 3 lone pairs, we have a negative charge. When we have 2 bonds and 2 lone pairs, we have a charge of 0. When we have 3 bonds and 1 lone pair, we have a positive charge. So if we work some of the examples shown below, we can first try and do these examples intuitively by thinking about the predictive rules. And then what we can do is we can go back and count valence electrons. So if we look at F, we can see that the oxygen does not have a formal charge. There's 2 bonds, so according to our predictive rules, the oxygen has 2 lone pairs. Next, when we come to molecule G, we can see that the oxygen has a formal charge of +1. The oxygen has 3 bonds. According to our predictive rules, the oxygen has 1 lone pair. If we come over to molecule H, again the oxygen has a positive formal charge. It has 3 bonds, so according to our predictive rules, it must have 1 lone pair. Molecule I, which is ozone, has 3 oxygens. So if we start from the left with the neutral oxygen, we can see that it has 2 bonds. So it must have 2 lone pairs. The central oxygen has a positive formal charge. It has 3 bonds. It must have 1 lone pair. Finally, we come to the negatively charged oxygen. It has 1 bond. It must have 3 lone pairs. Molecule J, there are 2 oxygens again. Let's start with the oxygen that has the positive formal charge. It has 3 bonds, so it must have 1 lone pair. The ether oxygen is neutral. It has 2 bonds. It must have 2 lone pairs. Now if we count using the counting method, what we can see is that for oxygen it has a valence of 6. Now if we look at the oxygen, 1 electron comes from the bond of the 2 bonds here, so that gives us 2 bonding electrons. That means for oxygen to be neutral, we need 4 non-bonding electrons, which we have. If we come over to G, again, oxygen has a valence of 6. Here we have 3 bonds, okay, and a positive charge on the oxygen. So that means that the oxygen needs to have 5 valence electrons. 3 come from the bonding interaction. So therefore we are left with 2 non-bonding electrons, which we drew in. If we come to the hydronium ion, which is molecule H, okay, again, oxygen has a valence of 6, but we have a formal charge, so that means we need 5 electrons, 1 from each bond. That gives us 3 bonding. We are left with 2 non-bonding, which we drew in. For ozone, we have the 3 oxygen atoms. If we start with the neutral one, we need a valence of 6. We get 1 electron from each bond. That leaves us with 4 non-bonding, which we drew in. The positively charged oxygen, it will have 5 valence electrons, 1 from each of the 3 bonds. And then we were left with 2 non-bonding electrons. Finally, for this negatively charged oxygen, it needs to have 7 valence electrons to have that negative charge. 1 electron comes from the bond. We are left with needing 6 non-bonding electrons, which we drew in. For molecule J, the top oxygen has a positive formal charge. It needs to have 5 valence electrons, 3 of which come from the bonds. So we are left with 2 non-bonding electrons, which we drew in. This oxygen here for the ether has 6 valence electrons because it has 0 formal charge. 1 electron from each bond. We are left with 4 non-bonding, which we drew in. So we can also do these rules for nitrogen. Nitrogen has a valence of 5. So when nitrogen has 2 bonds and 2 lone pairs, it is negatively charged. When nitrogen has 3 bonds and 1 lone pair, it has no charge. And when nitrogen has 4 bonds and no lone pairs, it has a positive charge. So again, let's go through the similar exercise for these molecules below that we did for oxygen. So let's try and use our predictive rules first to draw in our lone pairs, and then we can go back and count. So this nitrogen here, for E, has a negative charge. That we have 2 bonds, so we must draw in 2 lone pairs. The nitrogen in molecule F has no formal charge, so it must have 1 lone pair. For G, we have a positive charge on that nitrogen. There are 4 bonds. We don't need to draw in any lone pairs. For H, we have 2 nitrogens. One with a positive charge. It has 4 bonds. We don't need to draw in any lone pairs. For the nitrogen, it has a 0 formal charge. And even though the bonds to the hydrogen aren't drawn in, there are 2 of them, so that nitrogen has 3 bonds and it needs 1 lone pair. Now if we go back and count and we start with E again, we know that nitrogen has 5 valence electrons. It has 2 bonds, so that 1 electron comes from each bond. The nitrogen is negatively charged, so it must have a valence of 6. When we subtract the 2 electrons from the bonds, we are left with 4 non-bonding electrons, which we drew in. For F, this nitrogen is neutral, so it has a valence of 5. We get 3 electrons from the bond. We are left with 2 non-bonding electrons, which we drew in. For molecule G, we can see that the nitrogen, neutral nitrogen, has a valence of 5. We have a formal positive charge, so we have a valence of 4. 1 electron from each of the 4 bonds. There are no lone pairs. For this positively charged nitrogen, again we have a valence of 4. 1 electron from each of the bonds. No non-bonding electrons on that nitrogen. For the neutral nitrogen, nitrogen has a valence of 5. We get 1 electron from each of the bonds. We are left with 2 non-bonding electrons, which we drew in. So again, you can either do this by intuition, where you use the predictive rules, or you can count. So nitrogen and oxygen aren't the only atoms that can have a positive charge. We can have carbons that exhibit a charge. And now, if we look here, okay, we can try making our own predictive rules for carbon. If we look at molecule A, where that carbon has a negative charge, okay, it has 3 bonds. Carbon needs an octet, okay, so we can draw in a lone pair. For the positively charged carbon here, okay, we have 3 bonds. We're not going to draw in any lone pairs. And then here, for this negative one, we're going to draw in a single lone pair, okay, and another lone pair here. There are several neutral carbons in molecules A, B, C, and D. Okay, what's not drawn in these bond line structures are the hydrogens. Okay. So if we were to write predictive rules for carbon, when carbon has 3 bonds and 1 lone pair, it has a negative charge. When carbon has 4 bonds and no lone pairs, it has a 0 formal charge. When carbon only has 3 bonds and no lone pairs, it has a plus charge. And if we look at the valence where we count, we can prove this to ourselves. So let's go back to A and deal with this carbon that has the negative charge. Carbon has 4 valence electrons, but here it has a formal charge of -1, so it must have 5. We get 1 electron from each bond. We are left with 2 non-bonding electrons, which we drew in, the 1 lone pair. Here for this positively charged carbon of B, carbon must have a valence of 3. We get 1 electron from each bond, so we don't need any lone pairs. If we come to this negative oxygen again, it must have a valence of 5. 1 electron from each of those bonds equals 2 non-bonding electrons. And the same can be said for the negative carbon of D. Just to take the neutral carbon as an example, I'll circle it in A. Okay? Carbon has a valence of 4 when it is neutral. We have 1 electron from each bond, so there are no lone pairs, and the carbon has a formal charge of 0. So this concludes how we determine formal charges and lone pairs on bond line structures.